Good morning, everyone, and happy Thursday. Hello, and welcome to our webinar on Softree Optimal for Earthwork Cost Reduction and Feasibility Testing. I'm Erin Wozni. I'm the Business Development Manager over here at Softree, and I have the pleasure of introducing Craig Spears. He's one of our software engineers, and he'll be doing the lion's share of today's webinar. I just wanted to go through a couple of pieces of housekeeping before we get started. And then finally, this is a bit of a new one for us, we're actually going to be doing today's webinar in beta software. So this contains all of the features and functions in the current release that Craig is going to be showing you. However, you may notice there's a couple of things that are a little bit different, including the ribbon interface, the 64-bit platform, and you may take notice to the GPS tabs. These are some of the new features among many others that are coming in our next release. So today's objectives for the webinar, and then I'll stop talking and hopefully the echo will completely go away, are to demonstrate how to use Softree Optimal and its real-time costing data to reduce earthwork costs, as well as to demonstrate how to quickly check the feasibility of an alignment for your constraints. So really it boils down to Craig's going to be giving you a quick how-to on Softree Optimal to achieve these two primary objectives. Before we go over into the software, it's kind of important to have a bit of an understanding of what goes into optimization. And there's really 5 key buckets that go into it. The first being the existing ground, and we recommend here at Softree wherever possible to recommend using lidar data because of its accuracy as well as just the general scope is significantly larger than with most other survey data. You need your preliminary horizontal alignment or horizontal alignments plural. And as Craig will show you today in this webinar, you can actually compare the relative costs of 2 different horizontal alignments quite quickly using Softree Optimal. You're also going to need your cross-section geometry, so a bit of an understanding of what template, if you're familiar with Rota's template, or what assembly you're going to be using if you're familiar with Civil 3D. And then the most important 2 buckets, and these really are the cornerstones of what makes optimization work and work well. And that's your costs and your constraints. And I'll just take a second to go through both of those. So in terms of the costs, some of the things that the optimization tool looks at are your cut-fill costs for your subgrade and surfacing materials, your movement loading costs, as well as your movement costs in general, and additional costs such as culverts, pit opening costs, and costs for things like clearing and grubbing. Now, it might seem a little bit daunting at first with this large list of costs that you're going to need to put into it, but don't worry, we have default costs, and those can be used quite easily. They're available in the software, and they're really good for relative comparisons. So even though they're not exact to your organization, they work really great for being a relative comparison tool between 2 different alignments. And then the other piece is constraints. And these are, really important in terms of making sure it is a real-world alignment. And this is where it's important for the engineer to be very involved in the tool. So we've got our min and max grades, minimum K values, your control points, so whether that's elevation or grade, if you need to have full bench sections, material movement directions, and then borrow and waste sites. From there, it goes into optimal, and yes, it may seem, and Craig will show you this, like it's pushing a button. However, it does a lot of stuff depending on those inputs, and Craig will go into this in much more detail. And I'm going to stop at that point now, pass it over to Craig, and hopefully get rid of the echo for everyone.
Thanks, Erin. Just going to show my screen here, do a switch. There we go. I hope everyone can see my screen now. So I always struggle a little bit with doing sort of general presentations like this on what kind of a project to use. I'm pretty certain that we have a variety of different types of applications out there that people want to address. And so it's very hard to find one project that does it all. What I've come up with is a road project, a resource road project that was from a recent training we did in Oregon, and it's a very low standard road. It's not a super expensive road. Everything that I show you would apply to a higher level civil public road or highway. What I've actually found is that the civil type projects actually work a lot better in Optimal. They produce more significant savings than do lower standard roads. And the reason for that is a lower standard road generally will follow the ground a lot more, and it's easy for an engineer to figure out that, or it's easier. And so, I mean, typically we see in a resource road improvements of 10 or 15% on earthwork, sometimes more depending on the situation. And in a public road or highway of a higher standard, we usually see more than that. Surprisingly, we'll see 20, 30 or higher is often the case, an improvement in what the optimized design can do over the engineered design. So it's kind of interesting. But in both cases, it's very clear that optimization is quick. If you follow the correct workflows, you can do things very quickly, and that alone gives you the opportunity to look for better solutions, find better solutions, and save costs that way, construction costs as well as engineering costs. So that's my preamble. So this particular project, it's in feet. It came from Oregon, so it's in feet, and it's about 3/4 of a mile long road. Relatively steep grades. They get up to about 15%. It's a spur road that's coming off a mainline alignment, and it's heading up onto a ridge. And in the profile window, I've got the ground line, but I don't have any profile at all set. Also, this alignment, I think, was given to us. It was passed on to us by the organization that was doing the training, and it was based on lidar. And so, yeah, I'm going to now take that alignment, and I'm going to quickly show you what Softree Optimal can do with this particular alignment, and then we'll go from there. So first thing I'm going to do is create a new optimization. I'll just call it V-Align 2, and pretty much going to take all the defaults. I'll quickly mention that there are costs. I think Aaron mentioned this. There are costs associated with materials. I'll come back and describe that in a little bit more detail. And there's also constraints which control the road standard, the design speed, the minimum, maximum grades, and so on. And I'll discuss those a little bit more. Let's just go ahead and do this very quickly. I'm going to create an optimal profile for this alignment. And you'll see it's going to run. I just ran it before we went online here, and it runs and solves quite quickly. Optimization is a complicated process, and the tools that we've made have actually taken years of development with the university to put this together, actually more than 5 years. And so it's fairly sophisticated mathematics that's going on, and it's doing more than just balancing the road. It's actually minimizing the amount of cutting and filling as well as earth movement. So it's not just a simple balancing tool. It is much more sophisticated than that, and it will guarantee, subject to the conditions you give it, optimal. It will give you the lowest cost alignment. So there, it's finished, and you can see I've got a profile. Just zoom in a bit here. I can turn on the labels, and we'll just have a quick look. And where are my labels? Labels. Oh, I need to set it current. And there are my curve labels, and down here is the cost. The original alignment by default was the ground, and although it's obviously undrivable, the cost of just cutting and filling right along the ground, running that template around the ground, was about $80,000. Not huge. but for a resource road, probably representative. Now the alignment that's been optimized now, and now it is drivable. It's got nice smooth curves and grades that are reasonable. Its cost is about $40,000. One of the really nice things that you can do with the optimizer is say you're looking for an alignment, and you've come up with this one, and it's based on, what do we've got here? We've got sag and crest values of 20, so I know that it's going to cost about $40,000 with sag and crest values at 20. What if I increase the design speed? And this is the sort of thing that Optimal is great at. Okay, let's just bump the design speed and reprocess. See what it's going to cost. See what the difference is. Is it going to produce a better alignment that's not much more expensive? It's got to be more expensive because it's smoother and it's a higher design speed. But how much more is it? That question can be answered very quickly. So this dialog box is showing me what's called the optimality gap, which is, in the worst case, we now are at about 8% away from optimal. And at any time that I have an optimality gap, I can cancel and accept the solution, or I can let it continue till it finds the optimal solution. So there is a higher design speed alignment found very quickly. Compare it to, let me just compare this to the other. You'll see the two there. One's a bit smoother, one does a bit more cutting and filling, but it's a better alignment, and if you wanted a faster road, you found the solution very quickly. So that's kind of the push the button. There it is, optimal alignment. Looks pretty easy, right? It took 40 seconds to calculate an alignment. Sorry, it is easy. It is actually very easy, and there are a few things that you've got to watch out for, and I'm gonna explain some of those right now. But essentially, it is quite an easy process. The two things that I think you always have to be aware of when you're working with Optimal are speed. You can create problems that are quite large. It's doing very sophisticated things. And the other thing is feasibility, making sure that what you do is feasible. And let me go through some of the options here, and I can talk around those two issues as we go through some of the more detailed options about how Optimizer is working. So let's just have a look at the first profile we did, go into the options. And first of all, as Aaron mentioned, there's two key parts to optimization. There's a cost function, which is controlled in here, and the cost function works as there's a cost for excavation, there's a cost for embankment, and that is dependent on the materials. Over here you can see we've got multiple layers of materials. This particular design had fractured rock and clay, I think, mostly for layers. If you had something like solid rock, it was going to be very expensive to cut through or blast. So the optimizer will avoid that. It will really look for solutions that avoid that material because it's so expensive. So all of these costs are configurable. The interesting thing is it's been our experience that the costs aren't exactly critical to the alignment, that you can change these costs. As long as they're reasonable, you're still going to get a good alignment. And yeah, they're representative costs. They don't actually have to be exact. The other costs that are involved here are hauling costs, and those are broken down into free haul, overhaul, and end haul. And there's a cost for moving the material. So free haul, you typically have no loading cost at all. The material will be just cast about. or pushed. And then overhaul, you have a small loading cost and a more a cheaper moving cost. And then finally an end haul where material goes in the truck, larger loading cost and a smaller hauling cost. So based on those costs, it's going to look for an optimal solution. So that's one of the key parts of optimization. The other part of optimization is the constraint side of things. And what we do when we set up an optimization is to tell it to optimize within a certain vertical band. So I've said here to go 10 feet above and 10 feet below. That forms a band. And I want to form the band on the existing ground. If I had done the optimization several times, I could look at creating a band around one of the previously optimized alignments. So I'm just going to cancel out of here and show you what that band looks like. It's quite important to optimization. It's quite important to feasibility. So in our case here, just go to the constraints. There is our band. And the optimizer has to stay within that band. I can make the band bigger, of course, but there is a reasonable limit. You don't want huge cuts or fills, so you're going to set that band to a reasonable amount. Now, when you get into feasibility issues, the band actually plays into that quite a bit. If you were to try to make something even smoother here, you can imagine something that was so smooth that it would come outside the band and cause infeasibility. So the band is a very important part of understanding feasibility and constraints. The other thing, and this relates to speed quite significantly, is choosing this section sampling spacing. If you've got have to talk in metric, but if you've got a 15 or 20 kilometer road, you want to be very careful with the section spacing that you set. And here I've got 78 points selected. That's based on a 50-foot interval. My lowest point interval is 50 feet. If I went down to 5 feet, you know, oftentimes people will say, well, I want it really accurate, so I'm going to go down to 5 feet. It's going to cause the optimizer to have to do a huge amount more work. So choosing the section spacing is quite important when you're looking at using this in an operational way. You can give this the optimizer. The problems that I've done here have run in seconds. It's possible that it will take longer. For larger problems, you may even have several hours that it's grinding away looking for a solution. So you always want to keep in mind speed, and you always want to keep this issue of feasibility in mind. So just moving through the menus here, the second thing that you have to look at is the type of curves. And here we have different curve types. Polyline is for a very low standard road where you might only be interested, you're not even putting curves on it, you just want to have grade breaks. If I click on here, you can set the grade breaks. Basically the list is ordered, with one exception, is ordered in terms of speed. So I can create what's called fast curves, and if I did that, it's going to run faster, much faster. It's going to show me curves that have a minimum length, and essentially the curves will be back to back, so you won't have any tangents between your curves. It's not very desirable for most designers, but it's a very fast and quick approach to getting an alignment. So that's useful in early stages. The second one, which was the one I used, which was called curves and tangents, it's a bit slower, but in many cases it'll solve quite quickly, and it will produce a curve with a tangent, and you can set the curve length and the tangent length if you like as minimum lengths. The other one, variable curves and tangents, will actually move the position of the curves around, looking for for better solutions. It's slower. And the last one, which is actually very useful, is what's called user curves. So, and we use this quite often when we get a project from someone. They give us a project with a vertical alignment in it, and it's got curved positions defined. And we'll take those curved positions and optimize them. And what that's doing is it's saying, here are the positions of the curves, fine, just move them until they're optimal. So it's a very controllable way, but it does require that you lay out the curves before you optimize it. So there's several options. Again, the one I used is this one here, curve and tangent flow. The other very, very important things are the minimum maximum grades. Here I've got a minus 10%, which corresponds to adverse, my adverse grade coming loaded back from the end of the alignment, and my favorable grade of 15%. And I thought I had 20 in here to start with. Just check this. Yeah, I did. I perturbed it somehow. Yeah, so this is your K value, sag and crest K value. And yeah, based on this, it's going to form the road geometry. Then the next thing is control points. Typically, you want to add a control point at the start of the road because you're coming off an existing road. You could also enable the grade control at that point, which would allow you to make sure that your grade matches a grade coming off of some other road or intersection. Other control points that you might add are, let's just look in our case here. We actually have a culvert that we might want to make sure. So the alignment is run right through there. I want to set a control point up here somewhere. Let's say a couple of feet up. That's 2529 at 1915. So let's pop in a control point there. Actually, yeah, we'll do it in here. Control points at station, what did I say here, 1915. And I'll add a elevation at that point of 2529. And now I actually want to stay above that, so I'm gonna give it a tolerance. I'm gonna move the control point up 10 feet, and I'm gonna give it a tolerance of 10 feet. So I'll just simply shift everything up. So it's gonna go plus or minus 10 above this control, or around this control point. And yeah, so I'll add that. I'll also add the start of alignment. Do that. Let's just try now re-optimizing it. One of the things to workflows to follow with optimization is to start loose. Get a solution and work from there. So start fairly coarse and loose, and then start constraining the alignment. Oftentimes people have feasibility problems, and it's because they've over-constrained the problem. They've put in too many things that are virtually impossible to match, and I'll illustrate that in a second here. So it's found the alignment again, and hopefully we'll see it have moved up above our culvert. So we've actually, there it is. So now it's well above, it's found an alignment well above that minimum fill height that we wanted on that culvert. So that, if we looked at the band here, you see there's the band. It comes right up to the 2-foot mark above the culvert. Alignment had to stay inside that band. You put a control point. So there's various ways you can constrain the alignment. One of the things I quickly want to mention, suppose we did something that was impossible, basically. We said, well, we'll put a road up there, and I want the grades, I want it 8% grade going up there. I pretty much know from this that it's just not going to work. Let's get the optimizer to tell us this quickly. Unfortunately, there's this calculation, which probably didn't have to do, but it's fairly quick. And I think it's going to come back here and say, you can't do that. Yeah, could not find an alignment that would meet that condition. So back to the drawing board, maybe increase my alignment or increase my grade, and so on. So when you have a situation where you've got lots of things that you need to avoid, maybe utilities, you need to tie into driveways or intersections, and you want a certain design speed, it just may not be possible, and this will tell you pretty quickly if it is, and you'll have to relax that constraint to get a solution. So rather than fiddling around with the alignment for hours, this will tell you quite quickly if something is feasible. Other things to briefly discuss are pits. I didn't put any pits in which case if I don't have any pits, the optimizer will try and balance the alignment. If it can't balance the alignment without pits, it will tell you, and it'll move the material into an area called overflow. So you'll be warned that you've got an overflow or underflow, and the correct solution is to place a pit in. The other thing the optimizer does very well is if you've got areas where you can borrow waste material from and they're available, you can put them in here. Let's just do this. I'll create a pit, and I'll put it at the start of the alignment. And you can put an opening cost into the pit. So if you had to put an access road or something to get to the pit or to prepare it in some way, you could put a cost in there. You could put a distance that the pit is from the alignment, and you could also limit the quantity of material that can come or go to the pit. Pits can be either borrow or waste. And if you set up a series of these things, Optimizer will actually figure out which ones are economic to draw from or draw to. So it might be not always clear whether material should come from the pit or you should move it along the alignment. So it's very, very useful for doing that sort of thing. What else do I want to quickly mention? I wanted to show you another alignment. I just quickly mention here, oops, invalid field. I'm going to cancel from here. I've set this current, and it's pretty balanced. It's within what we call noise of the optimizer. It's got 40 cubic yards of material, and that's not balanced. Not a big deal. But we also have another output here. In fact, we have quite a few options for producing output for construction estimation. We have a graph here called OptiHaul, and I have to recost this, I think, to get it to work. Hopefully it's going to work. We're running beta software, by the way, Aaron mentioned. There we go. So this is showing me how material is being moved, and this first band here is freehaul. As you can see, there's a lot of freehaul going on, and this material is anything that's being moved above the freehaul distance, and it's showing me where the material is going. As well, you've got the mass haul. And of course, all this information can be output into a spreadsheet showing station from to materials and so on, in quite a detailed format. Okay, I'm going to switch gears a little bit here. Time is ticking on, And I'm going to switch over to another, well, first of all, I'll show you what I'm going to do here. We got this alignment, this horizontal alignment from the customer who we were training. I was just looking at it and saying, I wonder why, we've got this switchback in here, and it's actually got some fairly steep grades, maybe not super steep, but they're, they're getting up there, 15, oh, that's not that steep, 10% around the switchback area. Anyway, they're steepish, 12%. And so I wonder, could we flatten out those switchback areas and make this a bit more drivable without blowing the cost out? And so I said, well, I wonder if we put an alignment, maybe came around here, or drove further up on this road and then came off at a higher elevation. We honestly don't know much about this project. We just sort of get it and play with it. But anyway, so just to illustrate the point, I created another alignment. Let's go in here and I'll show you, turn on what it looked like. So I created that alignment. It came off, went a bit higher, came off. It's obviously gentler grades all the way up, and it got onto this ridge here. So that, I sketched that in, and now I want to compare it to this one, which I know is about $47,000. So I'll switch over here, and here it is. I've set it up, and by default, it's just running along the ground again, and it's quite, it's 78,000. So let's, using the same parameters, I'll optimize it. Just go ahead and process that. Again, it's not going to take very long. And very quickly, I'm going to get a cost for that other alignment. It's gentler grades, more drivable. And it didn't take me a lot of work to get that and to evaluate it. Again, I've got now a solution that is $34,000. That's actually cheaper already, and I've still possibly got a 6% improvement that I could look for now. So I can cancel this. I've got it, so it doesn't need to cancel. There's my profile. There's my cost, and yeah, this solution looks pretty good. I might, not knowing all the details, I might say, well, that's a good thing to do. So you get the idea. You can try things very quickly. You get a cost, and of course, all these things can be manipulated in this environment to tweak them. The optimizer may not give you exactly what you want, so you can come and tweak it. And so, well, for instance, I can move this curve. I can say we'll tighten it up a bit here. Oh, doesn't fit the tangents. Okay. And then re-optimize. Process. I've got a new curve, and it's pretty, you don't need to see it again, but I'll show you anyway. You get the idea. You can change the alignment horizontally, re-optimize, or you can just simply change it and recost it. So you'll get a new cost for that alignment and without re-optimizing it. So that's what we call real-time costing, and it's available. It's available alongside the optimizer. In fact, it uses the optimizer to calculate these costs. So this is pretty unusual, but I think I'm finished my presentation, Erin. Do we have any questions?
And yeah, if you want to just take advantage of the question panel in your GoToWebinar little panel on the side of your screen. You can type a question in there, and we'll just give it a minute or two to see if there's any questions. And if not, Craig, this is only 5 minutes over. You were one of our more notorious culprits for going over quite a bit more. So.
Yeah, I do sometimes ramble on for well beyond people's interest levels, but I can go on if people want. I could go for days, actually.
Excellent. Well, I don't see any questions right now, but if you do have one, by all means, you can reach out to us either through our website or through email. You can get us at support@softree.com. And, oh, Craig, sorry, one quick question that did just come in. Let me just pull this open a bit more. If a pit had a higher quality material than the common, how would you model it?
That's a great question. I didn't obviously get into all the details, but we have a concept here of quality. So you can specify what's called a quality index. So material has a quality, and you can tell the optimizer what qualities you can extract from a certain pit. You can also, if you look at the materials that are being excavated, you can apply a quality factor to each different type of material. So in this situation where I've got overburden, I've got a quality 1, quality 2. Now I can tell the optimizer I don't want to fill with quality 1 ever. I want at least quality 2 material, and the optimizer will then will not fill. It will remove the quality 1 material and send it to a pit and fill only with qualities of quality 2 or higher. Yeah, it's very flexible in terms of handling of different qualities of material.
Okay, excellent. And while that question was being answered, we actually got a whole bunch more, so we'll do our best to try and get through them all. One of the questions here was, is the Optimal program part of the normal road eng package? And I'll give you my quick answer, and then Craig possibly can add in a bit more, but elements of it are part of our normal road eng package. Design time costing and quick profile are available as part of road eng version 7. Optimal in its full scope, which Craig really took you through today, is available as an add-on to road eng, but it doesn't have any incremental annual support costs. So if you're a support customer, really nothing else extra you'd need to pay moving forward. There's just a quick add-on license perpetual thing that you do. So the next question after that, how does the excavation cost affect the end haul?
Excavation costs affect the end haul. Well, if you have to end haul, you have to end haul. The excavation costs will make everything more expensive if they're expensive. If you're on a steep slope, I didn't show you, but you can actually tell it if you must go to a full bench constraint. You can apply a full bench constraint, and then the cost of excavating will be calculated, and the cost of end hauling will be calculated. So you'll be faced with both costs, and the cost of end hauling is covered in the hauling costs. In here, you could have just 2 levels if you're a resource road. Or if you're a higher standard road, you might have 3 levels where this is a scraper, that this is your end haul. So that cost would be calculated based on those values and the distance the material had to move. And also the cost to dig it out of the ground is covered in the excavation cost. Am I answering your question? Have I got it right? Actually, I'd say maybe if you want to contact me after, we could discuss it in a bit more detail. I know it's a little hard to communicate through a funny little panel, and yeah, I'd be happy to explain that or talk more about how it does handle end hauling in more detail.
Excellent, and I think we've got time for one final question. So the last one here is, how do you set different subsurface, soil, and rock conditions along various stationings?
I like easy questions. Well, easy. Okay, so there's two ways. One way is really simple, and it creates a situation like what we have here, which is a constant depth surface, and you simply go into new interface design range. You go to subhorizons, and you tell it you've got overburden depth 1 on top of clay, depth 2 on top of fractured rock, and then you assign that to a range of stations or the entire road, as I've done here. So you can change these depths by station range, and it just does it. It sets the layer depths constant. If you've got if you've got some borehole information or geotech information, you can actually create a surface, a tin surface, and use that surface instead of these depths. So back here, assign by range, go in here. I can't, it's not giving me the option here because I don't have a surface set up yet. But if I did, I could specify a depth based on a tin surface. So you'd get a more detailed representation of the surface. So you have the two methods, quick and dirty, or a more detailed tin surface you can apply in here. That's it.
Excellent. Well, thank you, Craig, for taking everyone through Softree Optimal for earthwork cost reduction and feasibility testing. If you have any other questions, please reach out, and if not, have a great rest of your day. Thanks, everyone, for joining.
Thank you, everyone.